Lesson 13.2 is integration, the reverse process of differentiation. I would pause the video and write down these notes. Back in chapter 12, we talked about gradient functions, which was our derivative, which is a function that maps every x to its gradient of a specific function. So now we're going to talk about an area function, which is a function that maps every value of x to the area of the shaded region starting from a certain value up to x. So consider a positive and continuous function y equals f of t, so something like either of these functions here. And so we're looking at the interval from a to b. So the area enclosed between the graph and the t-axis and the vertical lines t equals a and t equals x is defined by a of x equals the integral from a to x of f of t dt. So we can actually find this function that represents the area in general using our integration. Here are a few more notes. I would pause the video and write them down. So if f of t is a positive continuous function, then the area enclosed by the graph and the x-axis in that interval can be defined by the definite integral a to x of f of t dt, where that thing is equal to capital F of x minus capital F of a, where the derivative, or capital F prime of x, is equal to our original function. So our new function's derivative is equal to our original function. This is called the antiderivative of f. So capital F of x is the function where its derivative is, again, the original function that we're now looking at. So for example, capital F of x is equal to 3x is an antiderivative of f of x equals 3 because the derivative of capital F of x is 3. And then same thing here, capital F of x equals x squared over 2 minus 3 is an antiderivative of f of x equals x because the derivative of capital F of x is x. And then same thing, capital F of x equals x squared plus 1 is an antiderivative of f of x equals 2x because the derivative of capital F of x is 2x. So it's kind of undoing itself. So antidifferentiation is the process of finding this antiderivative, which we use integration to do. So they undo each other. So this first example, we want to find an antiderivative of y equals 4 plus 2x. So we want to find a function whose derivative is y equals 4 plus 2x. So we want to think about the process that was done to get f prime of x to be 4 plus 2x and figure out what f of x would be to get that. So go ahead and pause the video and see if you can find an antiderivative of y equals 4 plus 2x. So to find a derivative, we bring the power down in front and reduce the power by 1. So if I have the derivative was 4, then what gives me a derivative to be 4? It would be 4x, because I would bring the power down in front, reduce the power by 1, the x would just drop away. If my derivative is 2x, what would have had to have been to get 2x? Well, I would have had to brought down the 2 in front, so that means my original power had to have been 2, and it would have just been multiplied by 1. So I end up with f of x to be 4x plus x squared. For this next example, it says find a function y equals g of x when the gradient function is dy dx is equal to 3x. So they're giving us the gradient function, they're giving us the derivative. Try and find g of x. So the function I found was g of x equals 3 halves x squared. So the way that I did it was I started with the x. If this is an x and that's my derivative, it had to originally have been an x squared. So I made this be an x squared, and then I thought, okay, if this was an x squared and I brought my power down in front, when I multiplied it, I got 3. What would it have had to have been before I multiplied the number by 2? So what times 2 is 3? It would have had to have been 3 halves. So g of x is equal to 3 halves x squared. Number 3 says consider the definite integral from 0 to x of 3 minus 2t dt, where 0 is less than x is less than or equal to 1.5. And for part A, we want to draw a diagram of the function f of t equals 3 minus 2t and shade the area represented by that definite integral. And then, by using antiderivatives, find an expression for the integral from 0 to x of 3 minus 2t dt in terms of x. So go ahead and pause the video and try this one. So for part A, I just drew the graph of the linear function 3 minus 2t, and then I shaded the region between 0 and some unknown value x, that's before 1.5. Part B, we want to find an area function that represents this area. So we have the integral from 0 to x of 3 minus 2t dt, and from the previous slide we said that this was equal to capital F of x minus capital F of 0, where capital F of x is the antiderivative of f of t. So if you haven't already done so, go ahead and pause the video and try and make an area function using antiderivatives. So I need to define the function whose derivative would be 3 minus 2t. Well, if it's a 3, that means that the original function was a 3x because the derivative of 3x is 3. If it was a minus 2t, that means that it originally had to have been an x squared. And then what do I have to multiply that by when it becomes a 2? And it would have just been a 1. So my original function before I took the derivative would have been 3x minus x squared. And then I'm going to subtract off plugging in 0 for x, and that whole thing is just 0. So my area function is going to be 3x minus x squared. All of these antiderivatives that we found, they are one possible antiderivative for the given function. Now we're going to talk more specifically about a family of antiderivatives. So if we're given that capital F prime of x is equal to f of x, then the integral of f of x dx is equal to our function before you took the derivative, f of x, plus c, where c is a constant real number. This is called an indefinite integral because we aren't given limits of integration. We aren't given a lower limit and an upper limit. So it's read as just the integral of f with respect to x, or f of dx. And this is called the constant of integration, this plus c on the end. So just like we had a power rule for derivatives, bring the power down in front, reduce the power by 1, we also have a power rule for taking integrals or antiderivatives, which is just the opposite direction. So if we have the integral of a times x to the n dx, we're going to raise the power by 1, so now we have a power of n plus 1, and then we're going to divide by the new power. And then we're going to add a plus c constant on the end. So for a derivative, we multiply the power down in front and reduce the power by 1. For integrals, we go the opposite direction. We raise the power by 1, and then we divide by the new power. And we have to add this plus c constant on the end, because if we were to take the derivative of this constant, it would be 0. It would go away. So you can have this plus any kind of constant, and it would still be the same derivative. So number 4 says find the family of antiderivatives of f of x equals 5. So we want to find all the possible functions, antiderivatives, whose gradient function f prime of x is 5. So go ahead and pause the video and try that. So f of x equals 5, that's really 5x to the 0 power. So if I apply the power rule, I'm going to raise my power by 1, so 0 plus 1, and I'm going to divide by my new power. So my new power becomes a power of 1, and I'm dividing by 1. So what function, when I take the derivative of it, equals 5? Well, that would be 5x. But then I could have had any constant on the end, because the derivative of a constant is 0. So we have to take into account the possibility that it's there. So our family of antiderivatives would be 5x plus c, where c is a constant. So go ahead and pause the video and try A and B for the next example. So for A, you want to take the integral of 4x dx. Well, that means x has a power of 1. So I'm going to increase my power by 1. And so my new power is 2. And I'm going to divide by my new power plus c. So I end up with 4x squared over 2 plus c, or 2x squared plus c, where c is a constant. For B, same thing. I'm going to increase my power by 1. So my power becomes 5 plus 1 is 6. And I'm going to divide by my new power plus my constant c. So x to the 6th over 24 plus c is the integral of my original function. Just like in derivatives, if you add pieces together, you just take the integral of each individual piece and write them as a sum of the integrals. So go ahead and pause the video and try C and D. So for C, I just took the integral of each individual piece and added them all up. So first one, x squared over 2, raise the power by 1, so it becomes a 3, and divide by the new power. Same thing with plus 3x to the first power, raise the power by 1, divide by 2. Negative 1 is the same thing as negative 1x to the 0, so raise the power by 1, it now becomes a 1, divide by 1, plus your constant of c. So you end up with x cubed over 6 plus 3x squared over 2 minus x plus c. For the last one, D, I can rewrite 4 over x squared as 4 times x to the negative 2 power, and now I can apply my power rule. So raise my power by 1, negative 2 plus 1 is a negative 1, so I'm going to divide by my new power, plus c. And so I end up with negative 4x to the negative 1 plus c, or negative 4 over x plus c. So raise your power by 1, divide by your new power, and then plus your constant of integration on the end. Number 7 says the curve y equals f of x passes through the point 1, 3, and the gradient of the curve is given by the function f prime of x is equal to 2 plus x over 3. And we want to find the exact equation of the curve. So first, they give us the derivative here, and we want to find the original function, so we need to find the antiderivative. And then we're going to use this point to help us find the exact value. So first, just pause the video and find the antiderivative of f prime of x equals 2 plus x over 3. So the integral of 2 is going to be 2x, increase the power by 1 from 0 to 1, divide by the new power, so you end up with 2x, plus x over 3, the integral of that would be x squared, raise the power by 1, divide by the new power, so x squared over 6, plus your constant of c on the end. So now we want to actually find what c is, and they give us this point on the curve. So we can plug that in and use that to help us find c. So plug in the point 1, 3 and find c. They give us the point 1, 3, which means it has to make the equation true. So I plugged in 1 for x and set it equal to 3. So you end up with 2 times 1 plus 1 squared over 6 plus c is equal to 3, which means that c is equal to 5/6. So our original function is f of x equals 2x plus x squared over 6 plus 5 over 6. Number 7 says if dy dx is equal to 2x minus 4x squared and y equals negative 1 when x equals 3, find y in terms of x. So go ahead and find the exact equation for y that gives you dy dx is equal to 2x minus 4x squared. So first I want to find the indefinite integral of 2x minus 4x squared dx. Increase the power by 1, divide by the new power, so you end up with x squared minus 4/3 x cubed plus c. And then they tell us that y equals negative 1 when x is 3. So I plugged in y to be negative 1 and x to be 3 and solved for c and got c to be 26. So my original equation, y, is equal to x squared minus 4/3 x cubed plus 26. The last example, it says find the cost function c of x when the marginal cost is m of x is equal to 1 plus 2x and the fixed cost is $40 US. So we talked about back in the derivatives chapter that marginal cost is the cost per unit, so it's the gradient function of the original cost function. So use this gradient function marginal cost to help us find the original cost function. So c of x is going to be the integral of m of x, or 1 plus 2x dx. So the integral of 1 is just an x, and then the integral of 2x, increase the power by 1, divide by the new power, would be plus x squared, plus our integration constant of c. And then they tell us that the fixed cost is $40. So no matter what, even when x is 0, you're still going to have to pay that $40. So I plugged in x to be 0 and set it equal to 40, and that just means that c is equal to 40. So therefore, our cost function c of x is going to be x plus x squared plus 40. So this section has been integration, which is the reverse process of differentiation. So looking at indefinite integrals and finding antiderivatives using integration, specifically looking at the power rule, increase your power by 1 and divide by the new power.